everybody. We're going to go ahead and get started. So last day I gave your test back. I think almost everybody was here and got them. If I didn't give it back to you, I can come to the lab section or you can pop up to my office to get it. I won't be able to stick around today to give any more back because today I run to my next class at 1 o'clock. So the only thing I thought I could really mention today is the final exam is coming. That is kind of scarily soon. I still don't have it made up, so I don't have specific details to give you. It'll be more or less like the term test, like not a lot of changes there. It's cumulative for the whole semester, so everything we've done since day one is fair game for the test. I tend to shoot to have it even throughout the course, but there could be just a little more towards the end of the course, like maybe one extra question towards the end, but you can expect stuff from the whole semester. Just like you were allowed to bring a sheet of notes into each of the term tests, you can bring the same sort of sheet of notes into the final exam. So that's about all I can tell you so far. I'm hoping to have it written certainly over the next couple of days, so I'll be able to give you a little bit more insight then. So any questions before we get going for today? Okay. So last day, the very last thing we did was we said that a current carrying wire makes a magnetic field. That's where we're going to pick up today, is talking about that magnetic field. We'll do as many examples as we can get through today, and then we'll have a new topic for tomorrow. So first question, what does the magnetic field around a current carrying wire look like? If you did this in high school, your high school teacher may have had a thing with iron filings to show you. So this is a 3D picture. This is a metal conductor with a little bit of current going through it. And the iron filings line up along the magnetic field lines. So you could use a compass to map out those lines. What the lines look like are circles around the wire. So kind of like this. At any given point, the magnetic field would be a tangent to those circles. So if the wire comes up this way, then the magnetic field at any one specific point kind of comes around like this. The 3D picture, of course, is hard to kind of draw and visualize maybe, so we can always switch to a 2D view. So if we take a top-down view, let's say the current comes up like this. If we take a top-down view, then the current is coming out of the page towards us. So that current would be represented by a little dot. And the magnetic field makes big circles around the wire. Magnetic field is a vector, so it has a direction. You get the direction of those magnetic fields with your right-hand rule. The way the right-hand rule works is you take your thumb, you put that in the direction of current. So when this picture is coming straight out at you, you make a circle with your fingers of your right hand, and that shows the orientation of the magnetic field. So those magnetic field circles are coming around counterclockwise. So that's the overall orientation. Your thumb comes up, your fingers are coming around this way. At any point on the circle, the magnetic field is a tangent to the circle. Some places those tangents are easy to look at and to draw. So for example, the magnetic field right here, the tangent to the circle, so that would just be straight down. So that one is not too tough there. So for right here, if we wanted the magnetic field at this point, it's a tangent to the circle. Right here it points this way. Sometimes you're off at an angle. Those tangents can be a little trickier to draw. What I suggest is if you draw the line from the wire to the point where you want the magnetic field, if you draw the radius of that circle, we know that a tangent is perpendicular to the radius. So if we wanted to draw the magnetic field, we can draw a line that's perpendicular to that R. So there's a line that's perpendicular. For our magnetic field, this shows we have two choices. It can either go up and to the left or down and to the right. Sometimes that's hard to figure out which one it is. So does it go up this way or does it go down this way? Here's where you use your right-hand rule. Your thumb is with your current. You make your circles with your fingers, and put your knuckles right on top of that point where you want to find the magnetic field. What are my fingers doing? They're going up and to the left. So So the magnetic field at this point is up and to the left and tangent to the circle. So there's the magnetic field. Circles to the wire, so the B at one point is tangent to the circle, which means perpendicular to the radius. So that's our right-hand rule. The magnitude of the magnetic field. So if you're interested in the derivation, your book does go through it. The magnitude of the magnetic field is a constant mu naught times the current I divided by 2 times pi times r. Magnetic field is a vector, so I'll put the vector sign on it, and I'll put RHR on there for we get the direction with the right-hand rule. For the symbols in this equation, mu naught. Remember when we did electric field stuff and Gauss's law stuff, we had epsilon naught. That was the permeability of free space, or the permittivity of free space. It talked about how electric fields move through a vacuum. This one is the permeability of free space. It's a descriptor of how magnetic fields can move through a vacuum. So this is a constant. It's equal to 4 pi times 10 to the minus 7 Teslas times meters divided by amps. I is the current through the wire. And R is distance between the wire and where you're trying to find the magnetic field. Okay, any questions? Yeah.
So, how is this different from the magnetic dipole that we were looking at for the lab there last week?
That is a good question. So the magnetic dipole moment, oh, this is a really good question actually. So the magnetic dipole is talking about loops of current. Okay, so this is a straight current carrying wire, and it makes magnetic fields in a circle. If you have a loop of wire, it still makes a magnetic field. To find the direction of the field, every bit of wire has a circular magnetic field around it. So ultimately, the direction of the magnetic field would kind of point up through the circle. You would get that by doing an integral around the circle of the wire. So that magnetic field would point up, and the magnetic moment essentially is a descriptor of that magnetic field.
So this is like we took a little piece of that wire of the loop, and we're just considering that little piece, kind of?
I would more say that this is our starting point, and if we wanted to find the loop, we take our straight wire and we turn that into a circle.
Okay.
Yeah, I would look at this as the start. And then this is not a bad place to come back to that question I asked before. And the question I asked before, it was a pre-class question. Think about the fact that a permanent magnet is something you stick on the fridge. So we get a permanent magnet just because it's a magnet. Or a current carrying wire makes a magnetic field. And how can those two things actually be the same thing? Anybody have any ideas? Okay, let's get into atomic structure, right? So kind of everybody knows basic atomic structure, right? So all atoms are made up of a nucleus. What flies around a nucleus?
Electrons.
An electron. Does an electron have a charge?
Yes.
Yes. Is that charge moving?
Yes.
What's moving charge?
Current.
Current, right? So every single little atom is actually a current. It's a current loop. So just like the current loops you talked about in the lab, and the current loops we can get when we talk about these sorts of things, electrons are little current loops. They make magnetic fields. In some materials, all of those fields line up. Most materials, they're all just random, right? One atom points this way, one points this way, and they're all out of order. Most of the time it all cancels. But once in a while, in some materials, they all line up. That's how you get a permanent magnet. So all the electrons basically line up. So that's how it's the same thing, right? So I think that's kind of neat. Yeah.
What do you mean by permanent magnet?
So picture you got a magnet you stuck to your fridge.
Okay.
Permanent magnet. Yeah. Okay, so that was a long answer to a short question. Yeah. Okay, so let's keep going. So let's figure out how to find magnetic fields, magnetic field vectors. I thought about trying to squeeze in all that magnetic moment stuff into the classes and torques and everything, but I kind of took it out in favor of doing more magnetic field examples. You know, it's always kind of a trade-off with how much you do in class. So, you know, I could do more stuff faster, but in general, people don't seem to like that very well. And fair enough, right? So let's say we have this current carrying wire. Let's find the magnetic field a distance 10 centimeters from the wire if the current is set 0.75 amps. So we can have two views here. Try and stick to that picture we looked at on the last page. So we can take a three-dimensional view, a side view. Our current goes up and we're trying to find the magnetic field right here, which is a distance of 10 centimeters from the wire. We call that distance R. R equals 0.10 meters. The 3D view, sometimes that's hard to figure out what the magnetic field looks like. So you have to look at this picture and ask what's the direction of the magnetic field at point P. So if you start by thinking this is my current carrying wire, the current is flowing up into the ceiling. The magnetic field makes circles around the wire. So this is what the magnetic field looks like around the wire, just like this. We're trying to find the magnetic field right here at this point. Okay, so it's a tangent to the circle. It either points towards you or away from you. You do your right-hand rule, your thumb goes with the current, your fingers are pointing away from you. So the magnetic field would be into the page at this point. So that's in the 3D view. So there's our magnetic field B. We found the direction from the right-hand rule. That sort of 3D imagery, that can be a little tricky to think about. So it's often, or it can be helpful, to take a top view. So let's look from here. So there's our current carrying wire coming towards us. And what it means is we've got our three-dimensional setup, and we're just tilting it so that we're looking straight at it, right? So now we're trying to find the magnetic field here at this point. We're still going to do our right-hand rule. Thumb comes towards you. We ask, what are our fingers doing right here at this point? It's a tangent to the circle, and my fingers are pointing up. So there's the radius, there's the distance, here's our R. We know that our magnetic field is going to be a tangent. Which is perpendicular to the radius. So that means our two choices for a tangent would have been pointing up or pointing down. But when we do our right-hand rule, our fingers point up, so it has to be up. And everybody okay? That's the basics of getting this part. Okay. So let's find the magnitude of the magnetic field. B is equal to mu naught times I over 2 times pi times R. 4 pi times 10 to the minus 7 Teslas meters over amps. Times our current 0.750 amps divided by 2 pi times the distance between the wire and the point, that was 10 centimeters. That gives us 1.50 times 10 to the minus 6 Teslas. There's our magnetic field, and the direction is into the page. And if we did an X, Y, Z coordinate system, you could also say B is minus 1.50 times 10 to the minus 6 Teslas, K hat. Something I'm going to recommend to everybody, and this is purely just a calculator thing. When you're trying to put this mu naught value into your calculators, sometimes people do this a little bit funny depending on your style of calculator. I'm going to suggest to everybody, you don't have to do it right now, but sometime before your next class, do this calculation, make sure you get this answer. If you don't put this into your calculator correctly, you're not going to get the right answer, and it'll give you a wrong answer on a test. It doesn't make a huge difference, but you won't be able to get 100 on your final exam. So just make sure you know how to do that calculation. Okay, we good to here? There was our easy example. So let's build on this example. let's say we have two wires separated by 5 centimeters. So there's our two wires. They each have a current of 0.75 amps, but one is up and one is down. Find the magnetic field at point P, which is 5 centimeters from this wire right here. So we've got two wires, let's call them 1 and 2. Wire 1, wire 2. So we can stick with our side view if we wish. So if we have two wires, we know it makes two magnetic fields. To find the total magnetic field, we need to find the field of each one, remembering that it's a vector, and then do that vector sum to get the total magnetic field. Wire 1 is not too bad because it's what we just did. So wire 1 was a 0.75 amp current. We found the magnetic field 10 centimeters away. That current pointed up. That's exactly what we had right here. So for wire 1, we know that the magnetic field made big circles around the wire. At this point, the magnetic field pointed into the page. There was our B1. And B1 we found was minus 1.50 times 10 to the minus 6 Teslas K hat. And then from our top view, there was wire 1. The magnetic field was a big circle around the wire. The direction of the magnetic field at this point is coming up. There's our B1. So there it was in our top view. Okay, this is what we did on the last slide. So now we'll add this one to it, wire 2. Wire 2 is only 5 centimeters from our point. We're probably anticipating that wire 2 is going to have a bigger magnetic field because it's closer. So let's see if we can get the direction. So the wire has current that's flowing down. So your thumb comes down. You're trying to find the direction of the magnetic field over here on this side. Make a circle with your right hand. What are your fingers doing at this point? They're coming out towards you. Okay, so there's our 3D version. If you want to tilt it for your top view, then at this point the magnetic field points down. That makes sense. The current is in the opposite direction. The magnetic field is in the opposite direction. Okay, so the magnetic field around this wire is a big circle that comes like this. And the direction comes around this way. So it's out of the page right here. There's our B2. Over here, the current is flowing into the page, going away from you. The magnetic field makes a big circle around the wire. The orientation of those circles comes around like this. The magnetic field at this point, straight down. Everybody okay with the direction? So now we'd like to find the magnitude of that magnetic field. So there's our distance between the point and wire 2. We'll call that R2. The magnitude of the magnetic field is mu naught times I2 divided by 2 times pi times R2. So 4 pi times 10 to the minus 7 Tesla meters over amps and 0.750 amps divided by 2 times pi. R2 is from the wire to the point. Our picture tells us that that's 5 centimeters. That gives us a magnitude for B2 of 3.00 times 10 to the minus 6 Teslas. So that's the size of that magnetic field. When we look at this picture, we see that the direction was out of the page. So B2 equals 3.00 times 10 to the minus 6 Teslas out of page. Out of page corresponds to positive Z direction. So we could also say 3.00 times 10 to the minus 6 Teslas K hat. Then for our total magnetic field, we just add those together. So we get minus 1.5 times 10 to the minus 6 Teslas K hat, plus 3 times 10 to the minus 6 Teslas K hat, to give us plus 1.50 times 10 to the minus 3 Teslas K hat. So there's our total magnetic field.
basically, the magnetic field would be going in the J direction, positive J direction and the negative J direction. Would that change the answer?
Let me see. So if you wanted to forget about this picture, that would be fine. But you just have to be clear sort of what coordinate system you're talking about. My X, Y, Z here goes with this one, right? So in this one, my currents are flowing up and down. Positive Y is up, X is to the right, and Z is out towards you. When I tilt it to my top view, it changes the coordinate system, right? I'm looking at the top of the Y-axis. You just gotta be really careful about your coordinate system, that's all.
Because you're gonna get the opposite sign if you use the other coordinate system. That's gonna be in the J, and that's gonna be negative. That's the bigger one, and it's down.
Yeah, and it comes from tilting the coordinate system.
Okay.
Yeah. Yeah, so if you wanted to forget about this, no problem. Just be clear about what you're doing. Okay, so those were pretty straightforward. That was just up and down stuff. So let's go to one with an angle. And there's more practice about this stuff on your assignment as well. I don't like to take forever in class because I figure it's kind of boring to watch, so I'll just try and do the more interesting examples. So I've got a magnetic field with a current of 1.25 amps into the page at a distance of 10 centimeters above the origin. Find the magnetic field at this point over here, 10 centimeters on the x-axis. So the first thing we want to do is let's think about what does the magnetic field look like. Our current is going into the page. The magnetic field makes big circles around the wire. So in the process, the first thing you do is you draw a big circle around your wire and make sure your circle cuts through point P. So that step is pretty important. So our magnetic field makes a big circle. We'll draw the circle. Let's get the orientation of the circles. So my thumb is into the page. My fingers are coming around this way. That's the orientation of the magnetic field. My magnetic field at point P, this one is not up or down, left or right, so this one can be a little bit trickier to draw. I tend to draw them with a ruler just because I'm like that. You don't have to, but I think I will take out my ruler all the same. So if you want to be sure you're getting your magnetic field right, you draw a line that connects your wire to your point. You're drawing a radius of the circle. So there's your R. Your magnetic field is a tangent to that. So I'll draw my tangent line to the circle. Then you have to decide, does the magnetic field come up this way or down this way? There's where you use your right-hand rule. So you put your thumb with your current, you lay your knuckles on top of your point, and you ask which one does it go with, and it goes to the one that points down in a way here. So this side here is the one that is your magnetic field. Magnetic field B. When this is a test question, part A tends to be draw the magnetic field. You don't have to be perfect, but I'm certainly looking for it to be in the right quadrant. You know, it can't be pointing the wrong way, and that's something I'm looking at for sure. As much as possible, you should be making sure that the B and the R, you know, are close-ish to perpendicular. You don't have to have your protractor there, but it's got to look perpendicular. If you draw it like this, I'm not giving you full points for that, right? That's not perpendicular. Draw it like this, yeah, that's probably fine. Like that, super. Okay, so there's what our magnetic field looks like. We can go ahead and find the magnitude if we wish. That's pretty easy to do. So the magnitude of the magnetic field is mu naught times I over 2 times pi times R. Mu naught is 4 pi times 10 to the minus 7 Tesla meters over amps. Times our current 1.25 amps. Divided by 2 times pi times R. R is not a number we're given in the picture, but it's certainly something we can figure out. If we look at our triangle here, so that's 10 centimeters, that's 10 centimeters, this is a right angle, R is a hypotenuse of a right angle triangle, so we can find our R value. So R is the square root of 10 centimeters squared plus 10 centimeters squared. Which gives us 14.1 centimeters. Convert that to meters. And the size of our magnetic field is 1.77 times 10 to the minus 6 Tesla. There's the size of the field. We have to remember that our magnetic field is a vector. The vector nature is important, so you have to write your answer as a vector. There's two ways to do that. You can use the polar notation or the unit vector notation. So let's see if we can get the polar notation without doing too much work. If this is a right angle triangle and the two legs are identical, then what's this angle in right here? That gotta be 45 degrees, right? That's the sort of thing you can just go ahead and write on an answer. You don't have to prove that's 45. You know, at this kind of point in the math that you have studied, I sort of expect that people just know this. Okay, so this one is 45. If R and B are perpendicular, and this one is 45, what's this angle? Also 45, okay? Again, something I pretty much expect you to just know. You don't have to go ahead and prove those things. So if you get simple angles of 45, no problem. So we can write our answer. B equals 1.77 times 10 to the minus 6 Teslas at 45 degrees below the negative x-axis. Questions? Yeah.
You say negative x-axis because of the direction that it's in?
Yeah, because it's left. It's down in the third quadrant. To roll you into the next question, the one that comes after this, I'm leaving for a homework question, and it asks you to find the sum of two magnetic fields. For that part, you're going to have to do a vector addition, which means you're going to need components. So let's go ahead and make sure we know how to find the components from here. So if we're going to do components, we should draw the x and y components of our B vector. So the y component comes down. There's our by. Our x component comes to the left. There's our bx. And we use our trigonometry sine and cosine to find the two components. So bx points to the left, so it's going to be negative. So it's minus b times cosine 45 degrees. So bx is equal to negative 1.25 times 10 to the minus 6 Teslas. Our y component points down, so that's also negative. That one is adjacent or opposite the angle, so we use sine. Sine and cosine of 45 have the same value, so our y component is the same size as our x component. And then just to clue it all up for a nice answer, if you had wanted to give your b in unit vector notation, you would say that b is equal to minus 1.25 I hat minus 1.25 j hat times 10 to the minus 6 Teslas. On a test, I don't tend to specify what kind of vector notation to use. Polar, unit vector, you know, they're equivalent. So if I don't specify, you can use whichever one you prefer. I tend to use whichever one's easier. Okay, questions? Okay. So the homework question that comes after this one is we keep this wire here, we put another wire in, find the total magnetic field. So I'll post the solution for that one. And then the next slide in the notes I've got the same situation and I'm asking you to find where is the total magnetic field 0. For this one, I've got a video solution done up. I'm gonna post that one on Brightspace rather than go through it in class, just because I got a couple more examples that'll help you more with the assignment. This one, you might remember that we did something similar with the electric fields. So we said, where is the total electric field equal to 0? And we had to think about the directions of those vectors. We had to get them equal and opposite. You've got to do the same thing here. You want a place where the two magnetic fields are equal and opposite. So I will leave that for you. And then we will move on to this one, which is probably a little bit more challenging. So a better choice to do in class. So we have 4 long straight wires. We're already taking a top-down view. They each have the same magnitude of current. 1, 2, and 3 all have currents floating out of the page. And wire 4 is into the page. And our 2 questions are, what is the magnetic force on wire 2? And what is the magnetic field at the center of the square? Those are 2 separate questions, so they don't build on each other. They're 2 different questions. We'll get started with the first question first. So we have to think carefully about what we're trying to find in the first question. So what is the magnetic force experienced by wire 2? Wire 2 is a current carrying wire. We know that current carrying wires will experience a magnetic force which is equal to the current of the current carrying wire, so I2, times the length of that wire L, crossed with the magnetic field that it's sitting in. So to date, our magnetic fields, we've just written them down as a number with a direction. That's all we've done so far. Here we introduce a new factor, which is the fact that wire 1 makes a field, 3 makes a field, 4 makes a field, and wire 2 sits in those 3 fields, right? So this magnetic field here, this is a result of those 3 fields added together. Okay, so 1, 3, and 4 make fields. Wire 2 sits in the field, so it feels a force. Okay with the idea? Okay, so we got lots of work to do here. You can do this problem in kind of one of 2 ways. You could find the field of wire 1 and then find the force due to wire 1. You could find the field of wire 4, find the force due to wire 4, and then likewise with 3 and add the 3 forces up. So you could do the forces sort of by each. Or you could find the net field and then come and find the net force. I'm going to do it that second way. To me, it just kind of flows a little bit better. So let's get the direction of the magnetic field at wire 2 because of each of the other 3 wires. So wire 1 has magnetic fields that make big circles around it. I can try and draw it, but it's going to get real messy real fast. So there's the field around wire 1. My right-hand rule tells me it comes around this way. A tangent to my circle at point 2 is going to point straight up. So that's the magnetic field due to wire 1. Everybody okay with that? We've sort of done that already. Okay, 3 next. Magnetic field due to wire 3 makes big circles around wire 3. Something like that. The tangent right here at wire 2, we use our right-hand rule. Circles come around this way. The direction of the field this way is going to point to the left. And then wire 4, that makes circles that come around this way, so let's draw those circles. Something like this. Our right-hand rule says that the circles come around this way. And then we need to draw the tangent to the circle. You might be able to see that. You might want to get out your ruler and measure it. So there's the distance between wire 2 and wire 4, the radius of that circle. The magnetic field is a tangent to that and coming down this way. So there's our B4. Okay, that was a lot of work all in one go. Any questions about any of those directions? So you draw your circles, you know, you want a tangent to the circle at the point, and you use your right-hand rule to pick exactly which direction, up, down, left, right, so on. Okay, so let's find each of those magnetic fields, then we'll do the vector addition. That's gonna give us the total field that we can put in here and find the net force. So that's where we're going with this. So for our first one, B1, so B1, here's wire 1, here's wire 2, here's our point. The magnetic field made our circle, the tangent right here. B1. The magnitude of that field B1 is mu naught times current 1 divided by 2 times pi times the distance between the wire and the point. The picture doesn't give the size length of the square, so I'm just going to go ahead and call that A. So R equals A. Mu naught says each one has a current of magnitude I divided by 2 pi R, 2 pi A. We know that that magnetic field points straight up, so I'm going to put that in the J hat direction. Any questions there? All right, so we use the equation and the right-hand rule to find that magnetic field. Let's do B3 next. So B3. So my wire 3 is down here, my point is right here. The magnetic field makes a big circle coming around the wire. The direction was to the left. B3. The magnitude of B3 is mu naught times I3 divided by 2 times pi times R. I3 carries the same current as the rest of them, that was just called I, over 2 pi R. That's the side length of the square, so that was just A. That one points to the left, so B3 is minus mu naught I, 2 pi A, I hat. Okay, so to the left was negative A, I hat. Still good? Okay, so that's 1 and 3. Now we'll do 4. This looks a lot like the one we just did in the previous example. So wire 4 was down here. Our point is up here. The magnetic field makes big circles around the wire. The tangent to the circle or perpendicular to the radius. Perpendicular here. We can find the magnitude of the magnetic field, just like we've been doing for all the other ones. So the magnitude of B4 is mu naught times I4 over 2 times pi times R4. R4 is a little bit more work, but not lots more work. So that's the diagonal of a square. This side length is A, this side length is A. So R4 is equal to the square root of A squared plus A squared, square root of 2A squared, or root 2 times A. So that's our distance. So B4 has a magnitude of mu naught times I over 2 pi times root 2A. I know mathematicians don't like root numbers in denominators. I'm a physicist, so I don't care. I'm going to leave it there. Okay. If you don't like it, then by all means multiply by root 2 over root 2. It will be fine. So we know we want to do a vector addition here. That means we'd like to have B4 in unit vector notation. We want to find the x and y components of B4. So it's got an x component that points to the right. It's got a y component that points down, B4y. It's a square, we're on a diagonal of a square, so that's 45 degrees, that's 90. This is 45 degrees. Just gonna zoom way in on the picture here. Okay, so this is the diagonal of a square, this is a right angle, so both of those have to be 45. R and B are at right angles, so this has to be 45 degrees. And our x component here, so up and down, left and right is at 90 degrees, so that has to be 45. Everything has to be 45 there. So to get our x component, b4x, that equals b4 times cosine 45 degrees. b4 is mu naught I over 2 pi times root 2a. Sine and cosine of 45. This is one of those numbers that I remember. Maybe you do, maybe you don't. Sine and cosine of 45, they're both equal to root 2 over 2. If you know that and put in root 2 over 2, that's fine. If you don't know it and put in a number, that's fine too. Okay, so either is good. I like it because those root 2's cancel. And then we don't have to worry if it's in the denominator anymore because now it's gone. So that gives us mu naught times I over 2 pi times a times 2. Everybody okay with the x component? Now we'll do the y component. b4y points down so it's negative. b4 times sine 45 minus mu naught I 2 pi root 2a times root 2 over 2. Sine and cosine are the same. Minus mu naught I 2 pi a times 2. So then if you wish, you can write your b4 as a vector. Probably strictly don't have to, but why don't we do it anyway? So we've got mu naught I over 2 pi a. So that's the same in both of them, times 1 over 2 I hat minus 1 over 2 j hat. So there's our b4 as a vector. To get our total magnetic field now, we're just going to add those three vectors together. So our total field B is B1 plus B3 plus B4. B1 was mu naught I 2 pi a j hat. B3 was minus mu naught I 2 pi a I hat. Now I've got my B4, which is plus mu naught I over 2 pi a times 1/2 I hat minus mu naught I 2 pi a 1/2 j hat. I have a lot of practice adding up unit vector stuff. I'm pretty comfortable putting this all in one line. If you prefer to stay with writing everything in their x and y components, like for example, if you wrote b1 x equals 0 and b1 y is mu naught I over 2 pi a, and just kept all your x's and y's together, did that sort of tabulation, that's fine. Or you can just do a shortcut and put it here in all one line. So we group our i's and j's together. So mu naught I over 2 pi a minus I plus 1/2 I plus mu naught I over 2 pi a j minus 1/2 j. So I grouped my i's and my j's there together. And that gives us for our net magnetic field mu naught I 2 pi a minus 1/2 I I'm just double checking because I feel like I made a mistake somewhere. I hate it if I make a mistake. Minus plus 1/2 j. questions? So now, we want to find our net force. So we're coming back to this one, I2L cross B for our net force. I2L cross B. I2, that was current I2. That one was flowing out of the page. So I2 is equal to current I out of the page, which is K hat. So we've got I times L times K hat crossed with our magnetic field, mu naught I, 2 pi A, minus 1/2 I plus 1/2 J. So there's all of our terms. I just want to simplify this a little bit. So I'm going to take this out in front of my K hat. I've got I times L times mu naught I over 2 pi A outside of K crossed with minus 1/2 I plus K crossed with 1/2 J. So for these bits inside, this is the same as minus 1/2 K cross I. K cross I is equal to plus J. And this one is the same as 1/2 K cross J. K cross J is minus I. So together these give minus 1/2 J minus 1/2 I. So then we can write our net force. I times L times mu naught times I over 2 pi A minus 1/2 I minus 1/2 J. Any questions? This probably kind of feels like a lot, does it? Maybe because it's all symbols? Okay, maybe I'll see before next class, can I sort of give this example again, but maybe break it down into bite-sized bits to help you walk through how you would deal with this as it came to a test? Okay, I'll see if I can get that posted and put up for a homework question, because I think maybe that would help walk through it as well. Yeah.
Did you simplify the i's to like an I squared?
Simplify the, oh yeah, I'd probably call that I squared L mu naught.
Okay.
Okay, so I'll do up that homework question. The other bits that I wanted to get through today, but we didn't get to because I already went fast enough, I'll post those with the notes and you can let me know if you have questions. And yeah, we'll quit there.